So just some background on what I'm going to be talking about. There's been some earlier work that carried out a large-scale comparative evaluation of existing state-of-the-art approaches for vaccine safety surveillance. However, these approaches may produce biased estimates based primarily on differences in patient preference. For example, whether a patient chooses to receive the vaccine or not, or when they choose to receive the vaccine, if they do choose to receive the vaccine. This might create further confounding that might not be captured by these existing approaches. So to deal with these confounding, Klein et al. In 2021 proposed a new approach called the concurrent comparator for vaccine safety surveillance with the motivation to control for this bias. So like the natural question is, how does the concurrent comparator approach perform based on real world observational health data? So a brief outline on the concurrent comparator design. The concurrent comparator design predefines a risk interval. So on the figure that you see on the right-hand side, this risk interval is going to be 1 to 28 days after vaccination. And it will match each vaccinated patient for whom you observe an outcome. So while the vaccinated patient is in their target risk period, which would be 1 to 28 days after their date of vaccination, if they have an outcome, they'll be matched to another vaccinated patient in their comparator control period, which in this case is going to be 29 to 56 days after vaccination. This is the period in which the vaccinated subject is deemed to be no longer at risk. And this matching is done on the same calendar date to take out seasonal effects. It's done between vaccinated subjects to take out other sources of confounding, like the ones I mentioned earlier. And it's also done based on gender, age group, race, and ethnicity. So after carrying out the matching, the estimation of the risk ratio is done using conditional Poisson regression. The overarching goal of our study is to compare the performance of the concurrent comparator with existing methods in the context of vaccine safety based on real-world observational data. There's clearly a literature gap on how the concurrent comparator performs in real-world observational data, which is what we're going to address. Comparison is based on some statistical metrics like type 1 error and power of detection, which are evaluated across time in a sequential way. So this time is going to be the surveillance period. We also consider the proportion of non-finite estimates returned by each method, which I'll come to later. To detect a safety signal, we are going to use the matched SPRT rule, which is well established in literature because this is a sequential setup. And we're going to consider 4 different designs: the concurrent comparator, of course, the self-control case series, the historical comparator, and the case control designs. To implement the concurrent comparator approach, our team has created an R package called Concurrent Comparator, which can be downloaded on GitHub from github.com/odyssey/concurrent comparator. Now, this package is, of course, open source and publicly available to download. And it has been extensively tested for any bugs by our team. I gave you part of the puzzle, which would be the statistical metrics and the methods. The rest of the puzzle is this. We're going to be considering different exposures of interest, for example, the H1N1 vaccine, different variants of the seasonal flu vaccine exposure, zoster vaccine, HPV vaccine, and 2 different COVID-19 vaccines. We will be considering 5 different data sources, of which the Optum EHR is an EHR, and the rest are claims databases. And our analysis will be based on an extensive set of negative control outcomes, to be precise, 93 of them, which are chosen by clinical experts. They are not believed to be related to any of these vaccines, and they have similar prevalence and percent inpatient diagnosis to adverse events. To evaluate power, we'll also be considering imputed positive control outcomes, which are imputed from the existing set of negative control outcomes and have known effect sizes, such as risk ratios of 1.5, 2, and 4, So just for context, the risk ratio of the negative control outcomes, they're all going to be 1. Given that this is a short talk, it's not feasible to cover all different variants of all the methods that we are comparing. So I'll be focusing on particular variants for each method in the literature, and we'll also be giving a small detail about each method. So firstly, we fix the time at risk for evaluating each method to be 1 to 28 days after exposure to the vaccine. This is fixed across the whole study. For the self-control case series, which constructs the counterfactual, asking how often did or do events occur in the same patients at different times, we'll be adjusting by age and season, excluding pre-vaccination window. For the historical comparator approach, which asks how often did events occur to other patients in the past when constructing the counterfactual, we'll be adjusting by age and sex using time at risk after historic visit. The case control design asks how often are patients with events vaccinated, and for this we'll be adjusting using the age and sex matched controls. So let's dive into the results straight away. First, I'll be discussing some differences in systematic error across these different approaches. So the setup is as follows. You have 2 different data sources, OptumEHR and Medicaid from top to bottom, and 2 different exposures, the COVID-19 and H1N1 vaccines from left to right. So, ideally, systematic error densities should be centered around risk ratio equaling 1 with 0 variance. So if there's no systematic error present, for all the negative controls, you should be getting risk ratio equaling 1. Like that should be the estimate. Like we can see that that's clearly not the case here. You can see like densities that differ considerably from this ideal scenario. Particularly for example, you can see the historical comparator and the case control approaches often positively or negatively biased from the null. But in general, we saw the concurrent comparator and the SCCS to be at least centered more or less around 1, often with lesser variance than the other approaches. What systematic error can do is that it can skew the type 1 error. It can considerably deviate from its nominal value, which we take to be 0.05 due to systematic error. And so given that there's systematic error present, there's a substantial amount often across all these approaches. We'll try to restore nominal type 1 errors or near nominal type 1 errors by carrying out implementing past work on empirical calibration. So I'll only be discussing results after empirical calibration. So these are some results on type 1 error across time. So this is a slightly busy slide, so let me summarize it for you. The setup is similar to the one on the previous slide. You have 2 different data sources, OptumEHR and Medicaid from top to bottom. And you have 3 different vaccines now, the COVID-19, seasonal flu, and H1N1 from left to right. As you can see, after carrying out empirical calibration, for most of the cases across these 6 plots, you have type 1 errors that respect the nominal threshold of 0.05 across time. But sometimes it can happen, for example, for the concurrent comparator in the seasonal flu case, for the OptumEHR data source, it violates. It goes above the threshold, right? We saw this phenomenon to be more common among the case control methods, that even after calibration, it can sometimes go above the nominal threshold. So after restoring near nominal type 1 errors of these approaches, we can compare the power of detection of these approaches. In this slide, we will consider the true effect size of the imputed positive controls to equal 2. So the true risk ratio is 2. And as you can see, for 5 out of the 6 plots here, the SCCS performs the best. It has the best power across time. However, for a lot of the cases, the concurrent comparator is pretty close to SCCS, and it actually performs the best for the seasonal flu exposure in the OptumEHR data source. You can also see that the performance of the concurrent comparator, or at least the relative performance of the concurrent comparator in terms of ranks, sometimes decreases when you're considering a smaller data source like Medicaid instead of a larger one like Optum EHR. This might indicate that the concurrent comparator requires a lot of data to give reliable estimates. As I said, we'll also be comparing the methods in terms of the proportion of non-finite estimates that they produce. So there might be various reasons why in a particular scenario you run a method and then you get a non-finite estimate. One reason could be that there's no subjects left after propensity score matching. And another reason, which is also common, is that there's no subjects at all having the outcome once you've constructed the counterfactual and you've matched. Just a brief result here, we consider the H1N1 vaccine exposures across two different data sources, Optum EHR and Medicaid. And we found the concurrent comparator to have a higher proportion of non-finite estimates than the other approaches. We saw this trend to be similar across other exposures and other data sources. This brings us to the concluding slide. So in our study, we compared the concurrent comparator approach with existing methods used in vaccine safety surveillance. Our analysis is based on an extensive set of negative control outcomes and imputed positive control outcomes based on these negative control outcomes with known true effect sizes, so we can calculate power of detection. This is done across multiple data sources and multiple exposures, like vaccine exposures. After carrying out empirical calibration to restore nominal type 1 error, it seems that for like most of the cases, we found the SCCS to perform the best overall. However, the concurrent comparator is often close to the SCCS in terms of power of detection. As I mentioned previously, the relative performance of the concurrent comparator can decrease for smaller data sources. And it might also produce more like frequent non-finite estimates, and we believe both to be tied with the fact that the concurrent comparator does carry out an extensive amount of stratification based on just the design as how it is. And that brings me to the end of my talk. Thank you for listening.